Let's talk about the mean value theorem. Now, we do want to stipulate that this is for derivatives. There is a mean value theorem for integrals, which I actually like to call the uh, average value theorem to differentiate that. So let's make sure that we're clear that this is for derivatives, not integrals. So here's what we're going to do. We're going to just take a graph, all right, and we're going to draw 2 points on the graph. Pretty simple. Now notice these points vary from 0 to 3 for x values. X equals 0 here, x equals 3 here. That's our horizontal range. What we want to ask is, what is the slope of the secant line on this interval from 0 to 3? Well, a secant line just connects 2 points, right? So we want to figure out what's the slope of this purple line. Well, you would figure out this point, 0, 1, figure out this point, which is 3, 0.25, and use the formula for slope, y2 minus y1 over x2 minus x1. So there's our two endpoints. Plug this in, y2 minus y1 over x2 minus x1. 0.25 divided by 3 is the same as 1/4 divided by 3. Okay. 1/4 divided by 3 would be 1/12. So the slope of this line, this purple line, would be 1/12. Now, that's the first part of the mean value theorem. What's the second part involved? Well, let's go ahead and ask ourselves this question. Can you find a tangent line on this interval, 0, 3, with the same slope as the secant line? So here's the slope of our secant line, 1/12. Is there some kind of tangent line on this interval that's equal to 1/12? Well, if we look over here, that's too steep, right? But as we get closer and closer, and I've drawn this blue line up here, blue point, sorry, it looks like we can find a tangent line right here that's the same slope as this secant line. Now, here's what I like to show my students. If we take this secant line and move it up, and in fact, I can do that right now, or visually, let's take this purple line and move it up. Okay, so it goes up, and this dotted blue line is kind of transition. Eventually, it will become the tangent line of some point on this graph. So this orange line is the tangent line at 1.5, 2. We can see it has the same slope as this secant line as we moved it up or down depending on the graph. So the answer is yes, we did find a tangent line by shifting the secant line vertically. But why were we able to do that? Well, let's take a look at a different graph. This is an absolute value graph because it has a V shape. Let's ask, what is the slope of the secant line on this interval 0 to 3? So let's draw a point at 0. That would be 0, 2. Let's draw label this point at 3. It's going to be 3, 2. What's the slope of the secant line? Well, you can see it's horizontal. So without having to do a lot of math, you can tell that the slope of the secant line is going to be 0 over 3, which is 0. So the slope of that secant line is 0. Can you find a tangent line on here? So remember, tangent line hugs the graph at one point. That's equal to 0. Try to shift this thing down, just like we did before, and see if we can find a tangent line that has the same slope as the secant line. Okay, well, if we try to shift this down, we cannot find a tangent line that has a slope of 0. Right here is not a tangent line because it doesn't follow the same slope of the graph. Okay, it's at the V, at the point, we know there is no tangent line. The answer is no. So what was the difference? Well, why could we find one for this graph, but we couldn't find one for this graph? Be thinking about that. Might want to pause the video and then come back. Okay, so no, we were not able to find a tangent line by shifting the secant line vertically. Why not? Well, the difference is that this is not differentiable everywhere. There is not a tangent line for everywhere on this graph. However, on this graph, it has a tangent line everywhere on this interval, and that's the key, differentiability. Mean value theorem, if a function is continuous and differentiable, this is important. When we talked about intermediate value theorem and extreme value theorem, we didn't care whether or not it was differentiable, but now we do. Okay, it's also on a closed interval AB, just like the other ones. Then there exists at least one value C on AB such that the slope of the tangent line f prime of C is equal to f of B minus f of A over B minus A, the slope of the secant line. As long as it's continuous and differentiable, then we can find a secant line that's equal to the slope of the tangent line and vice versa, but only if it's continuous and differentiable. Okay, now again, this is actually an existence theorem. So it just proves that there is a tangent line that's equal to the slope of the secant line. We might not necessarily be able to find it, but in our example, we are going to find it. Okay, another way to explain this is there is an instantaneous rate of change on the closed interval AB that's equal to the average rate of change on AB. That's all the mean value theorem is comparing a secant line and a tangent line and ensuring that those two slopes will be equal. Let's do an example. Is there an instantaneous rate of change equal to the average rate of change of f of x equals 2 to the power of x minus 1 on the interval negative 1, 3? If so, why? And if so, at what point is the instantaneous rate of change equal to the average rate of change? So not only are we going to try to show that there is a tangent line equal to the slope of the secant line on this interval, we will actually want to find what that slope is. And not only that, we want to figure out at what point instantaneous rate of change equal the average rate of change on this interval. So it seems like there's a lot going on here, but it's not going to be very difficult. Now, we can automatically say yes, it is, because this function is continuous and differentiable on negative 1, 3. And the mean value theorem guarantees this. How do we know it's continuous and differentiable? That might be a question you're asking. Well, this is an exponential function, so it's going to look something like this. Okay. Now, all we've actually done is just shifted it 1 unit to the right. And so if you know the parent graph of exponential functions, you'll know this is still going to be continuous even if you shift it. We know it's also going to be differentiable everywhere. It's always going to have a tangent line, and so that's how we know. It goes back to our understanding of exponential functions and what they look like. And it's certainly true for negative values as well. So yes, it is continuous and differentiable, and therefore the mean value theorem guarantees that there is some point on the graph where the slope of the secant line equals the slope of the tangent line and vice versa. First thing you're going to do when applying the mean value theorem is find the secant line slope. So the interval they gave us was negative 1 to 3, so we need to figure out the y value at negative 1 first. Plug this in. We get 2 to the negative 2, which is 1/4. So that's our first point, negative 1, comma 1/4. Second y value, we figure out plugging in 3. We get 4 back. So the second point is 3, 4. To find the slope of that line, we just do y2 minus y1 over x2 minus x1. It's going to become 4 minus 1/4 over 3 plus 1. So we get, looks like 15/4 over 4. And that's going to end up being 15/4 times 1/4, which is 15/16. 15/16. Okay. So that means the slope of our secant line on the interval negative 1 to 3 is 15/16. Maybe I should show that before we keep going. Okay, so we'll just have a point at negative 1, and we will have one somewhere on this graph at 1 at 3. And the slope of this line is going to be 15/16, close to 1. Okay, so we want to find a tangent line on this graph that's equal to that slope. So how do we do that? Well, in order to find the slope of a tangent line, you have to take the derivative of the original. Now we know that the derivative of 2 to the x is natural log of 2 times 2 to the x. In this case, we have an x minus 1. So it's natural log of 2 times 2 to the x minus 1. The derivative of the inside is just 1. So our derivative formula is natural log of 2 times 2 to the x minus 1. Now, how can we ensure that we find an x value where the slope is equal to the slope of the secant line? Well, if the slope of the secant line is equal to the slope of the tangent line, we can just plug in that 15/16 right in the place of f prime of x. Okay, in other words, f prime of x is equal to 15/16 in order for this to confirm the mean value theorem. Okay, so we're going to replace f prime of x with 15/16 since somewhere on the graph, the slope of that tangent line, say it's up here somewhere, was going to be exactly the same or parallel to the slope of the secant line. So this tangent line will have the same slope as the secant line, so we can replace f prime of x with 15/16 since we'll have the same slope. So that leads us to the next step. We're going to set the derivative equal to the average rate of change, or the slope of the secant line. Here's our derivative that we just figured out. We're going to be setting it equal to 15/16, since the slope of the tangent line equals the slope of the secant line, and then just solve. Now you might be wondering, how do I solve for this? Well, you can divide both sides by natural log of 2, first of all, or and then take the natural log of that, or you can just use your calculator. I ended up using my calculator. What I did was I subtracted 15/16 from both sides and got it over here. You can graph this equation and figure out where it crosses the x-axis. In fact, I'll go ahead and do that for you. There's a couple of things I want to point out here. When you're plugging into the x minus 1 into Desmos, you want to put that in parentheses, and then make sure you subtract 15/16 from that actual quantity. Also make sure you put a multiplication sign right here. Now when Desmos is great because when you graph it, you can just hover over where this crosses the x-axis, since we set this equal to 0, and we get 1.436. So this is the x value where the slope of the tangent line equals the slope of the secant line. Now, in order to figure out what that point is on the original graph, we will be taking this x value and be plugging it back into our original function, which was 2 to the x minus 1, to get a y value. So step 5 is to plug into the original to find the point. After step 4, which is solving for x, we plug in 1.436 approximately, figure that out again with the calculator to get 1.353. So that means at 1.436, 1.353, the instantaneous rate of change is equal to the average rate of change of the function on the interval -1, 3. And again, we knew it would exist because it was continuous and differentiable on that interval. Lastly, we will look at the graphical confirmation of this. Here was our original secant line. We found the slope of that to be 15/16. We took the derivative of our function, set it equal to 15/16 at this x value, plugged it back into the original, get this y value. And we can see that at this point, the slope of the tangent line is 15/16, which is equal to the slope of the secant line on the interval -1 to 3. Okay, that's it for the mean value theorem, which does involve derivatives. Make sure your function is continuous and differentiable on this interval. If you have any other questions about the mean value theorem, let me know.